All right, so yesterday we said that Lewis dot structures are nice, but they don't always describe describe a molecule very well, and that has to do with resonance, right? So we drew that one molecule where we said we would anticipate that carbon-oxygen bond in blue being shorter. The reality is it's the same length as the other carbon-oxygen bond, and that has to do with electron delocalization. So we have to be able to describe and explain resonance in a lot of these molecules in order to describe their reactivity and structure. So we went through two examples. The first one was the cationic example where that carbon on the right with the positive charge actually shares a positive charge with the carbon on the left. And then we saw another weird example where we had a carbon with a negative charge in a lone pair. And in this case, we said that it's not sp3, it must be sp2 in order to delocalize that negative charge. So that carbon doesn't follow our normal VSEPR rules. We have to account for the movement of electrons. So I'll show you guys some basic electron pushing rules that you can follow when doing resonance structures. The first rule of resonance is you don't talk about resonance. You don't break sigma bonds. Another way to describe a sigma bond is a single bond, right? In resonance, we saw we can move electrons, but those head-on overlaps aren't easy to move. It has to be occupied, or it has to be in a p orbital or a lone pair. So number 2 is don't exceed an octet of electrons around any atom in your resonance structure. The octet rule is still hard and fast here. You can have fewer than 8 electrons, but not more than 8. All right, third one's getting back to that first point. You only move lone pairs or pi electrons. All right, and then the last one is you use arrows to push electrons. And I'll show you how to do electron pushing. So typically we have some sort of electron source. This is going to be your pi bond or lone pair. And your electron arrow always starts from the source and goes to the location that the electrons end up on. And I'm going to put another note under here. Can't exceed an octet. Does that make sense? Oftentimes, students get this confused, and they want to show movement of protons, so movement of a H+ ion. That doesn't ever work in organic chemistry. We only show movement of electrons, not movement of protons, using arrows like this. So I'll show you a kind of cheesy example, and then we'll get into harder ones. So the first one I like to show people is with the blue horse. Is in resonance with a red donkey. And because they're in resonance, I have to bracket them, and I have to use that double-headed arrow. And what would their hybrid structure look like? What happens when a horse breeds with a donkey? You get a mule. What color should the mule be? A purple mule. This is confusing for students. Oftentimes students look at resonance structures and they ask, are they flipping back and forth really fast? A purple mule isn't flipping back and forth really fast, right? It is a purple mule. So the hybrid structure is an average of those two structures. Sometimes both structures are equal contributors, and so it's a true average. Other times, one of the resonance structures contributes more than the other. But it's important to remember that it's not flipping back and forth, that it's actually a hybrid average of the two. So let's go back and take a look at some of our example ones. So the first one we saw was that cation yesterday. And I want to do a bracket around it. And just like before, we need to do arrow pushing. So in this case, do I want to move that positive charge? No, we can't move positive charges. We can only move electrons. We don't have any lone pairs, but we do have a pi bond. So I'm just going to move this pi bond over to the adjacent carbon. You can only move pi bonds to the next door neighbor. It can't go any further than that. But when we do it, now the positive charge is located on this side. Sometimes what students will do is draw in all of the hydrogens. Let me slide this over. Just so that they can keep track of everything. And if this helps you, I would encourage you to do it, but it can help you to determine formal charge faster and easier. And it can help you to ensure that you're not violating an octet on any of the atoms, right? So we moved that pi bond over. We didn't move any of the sigma bonds. We didn't move any atoms. All right, what do you think the hybrid structure will look like? The sigma bond network's the same. Where's the pi bond? It's across all three carbons. So I'll just show this as a dashed line. And then oftentimes I show my partial positives like this and like that. So the two carbons on the end are sharing the positive charge. The carbon in the middle never had the positive charge, so we wouldn't include a partial positive on it. All right, let's do the same one that we did yesterday. I'm going to include all my hydrogens for right now. This one's a little harder. So now we've got this lone pair, and we've got a negative charge. All right, can I move the pi bond over like we did before?
Nope.
Why not?
Violates octet rule.
It would violate the octet rule, right? Let's just hypothetically draw what that would look like for right now, and then we'll erase it. Oops. So if we did this, this carbon right here has more than 8 electrons around it. That means that this isn't allowed. So we've got to find some other structure that would work better. So I'm going to keep this network in place. What do you think we should move if we can't move that pi bond? The electrons. All right, the electrons can only be dumped down. So I'm going to take these electrons and move them right there into that carbon-carbon bond and form a new pi bond. What's the problem, though? Then the middle carbon's got more than an octet. But we can fix that, though, right?
We could move the double bond at the same time.
Yeah. So occasionally you may have to use more than one arrow. So if I push those lone pair electrons into the carbon-carbon position, they'll form a pi bond. But then I must break that pi bond, and that pi bond can turn into a lone pair on the side carbon. So I'll do 2 lone pairs over here, the negative charge, and there we go. The hybrid structure looks a lot like the one above. We still have a delocalized pi bond, but this time we've got a delta negative on that carbon and a delta negative on that carbon. Does that make sense?
Why can't the middle carbon involve in this?
So there's no way to get a negative charge on the central carbon without violating an octet rule, which means that central carbon doesn't carry any of the partial negative. It's only the 2 side carbons. Does that make sense? All right, let's try a harder one. Let's try the carbonate anion. And I'm going to draw all my lone pairs just so we can keep track of octets. Am I missing any charges? Which oxygen?
The lower two.
The lower two, exactly. So these lower two actually have formal negative charges. So I'll go ahead and do that. Do a double-headed arrow. All right, what do you think I should do? We've got a few options here.
You can move the lone pairs into the bond with the carbon and then move the signal there up and the pi bond there up onto the other oxygen.
Yeah, there's actually like 3 different ways you can start this one. I'll just arbitrarily pick one for right now. All right, so I'm just going to pick this set of lone pairs. Can be dumped down into that bond. If we do that, though, that carbon now has more than an octet, so we need to free up some electrons. So we'll take this pi bond and move it up to that carbon. So now this carbon-oxygen bond is the double bond. This one's now a single bond, so I'll show 3 lone pairs here, 2 lone pairs here, and then this one was untouched. All right? But we can keep on doing this, right? So maybe I want to take this one, push that down. What should I do next? We got to free up some electrons, otherwise that carbon would have over an octet. So we'd maybe break the pi bond just like we did before. So now we've got a negative charge here and here. All right. What if I go ahead and dump one of these lone pairs back down and kick those up? Then I would really just be going right back to the beginning, right? You can show that if you want. It's really not expected that you show all of those arrow pushings, but this one has 3 main structures. Yep.
So electrons can only go down and pi bonds can only go over.
Yeah, so pi bonds can go onto the one side of the pi bond, or it can actually hop over completely, and I'll show you another example of that next. So kind of like up here, the top example, we moved a pi bond to the next door neighbor. That's acceptable, or you can move a pi bond onto an individual atom. The key is you can't have more than an octet. That's the number one thing you should look out for. Okay, so now we've got all of these structures. One question I get a lot from students is they'll say, aren't all of these the same? But just rotating, right? It looks like you're just spinning it. Kind of not. They are all similar. What they're called is degenerate resonance structures, meaning they're all equal contributors. But what we want to do is we want to look at that hybrid, right? So same thing that we did before. I'll draw my sigma bond network. But we know that this bond right here is a partial double bond, this bond right here is a partial double bond, and this bond right there is a partial double bond. So each of these oxygens shares that partial negative charge. So we need to show all of these resonance structures to account for it. And then if we were to assign a numerical value to those negative charges, what do you think they would be? The partial negatives, I should say. Would it be negative 1/3? It's a formal charge of negative 2, but it's shared over 3 atoms. So each of those would be technically negative 2/3, right? So sometimes we do run into it where all contributors are equal contributors, and if that's the case, they're called degenerate contributors. Does that make sense? Yes, so we had 2 formal charges, but they're shared across 3 atoms. So 2/3. So let's take a look at some weirder situations. We want to identify electrons that can delocalize. So I'm going to draw a partially condensed structure for this one. And I'm going to include all the hydrogens so we don't violate an octet rule. All right, what's this functional group with the nitrogen? An amine. Let's get a review. All right, so that nitrogen has a lone pair on it. I'm going to actually separate them out a bit so we can see them more clearly. There we go. All right, so let's take a look at how we could potentially draw resonance structures here. Can I move this pi bond over here? Why not? Yeah, the nitrogen would be overloaded with electrons. It would have more than an octet. So we've got to figure out other things we can move. If we can't move that pi bond, we've got to move the lone pair. So can I move this lone pair like that? Nope, that carbon would be overloaded. So we've got to move it over here. Whoop. So I'll just circle this and say, all right, it's got to move here. If that happens, though, the carbon that's next door would be overloaded, but we can fix that. What should we do?
We can move the double bond onto the carbon on
Yeah, exactly. So we can move the double bond, that pi set of electrons, onto that carbon, and it will turn into a lone pair. So CH3, this is now a double bond to that carbon. Single bond over here, got a hydrogen, CH3, hydrogen, hydrogen, and then our lone pair is there. We're missing some charges though. Where should the charges go on this molecule?
nitrogen.
So the nitrogen has a charge, should it be positive or negative?
Positive one.
Positive 1. So I'll just do positive. Is that it?
Negative on the carbon with the lone pair.
Yeah, negative on the carbon with the lone pair. So you can tell the formal charge hasn't changed between these resonance structures. We've just showed electrons in a different location. Okay, so now what I want us to do is to look at the nitrogen and ask ourselves, what's the hybridization of that nitrogen? What do you guys think? Why sp2? Yeah. Some people would argue, though, this one has a steric number of 4.
Does it have to be in the orbital for the orbital?
Yeah. If you remember, those lone pairs, in order to delocalize, must be in a p orbital. If they're not in a p orbital, they can't delocalize. So the reality is this nitrogen must be sp2. In order for the electrons to delocalize. All right, now what I want to do is draw a hybrid. Okay, so same sort of thing. I'm going to draw my backbone, but we want to use dashed bonds and partial charges. So let's see if we can get this. Where should the dashed bonds go? Yep, between basically all 3 of these atoms. We could show that as a dash bond. So they're not quite a single bond, not quite a double bond. All right, this nitrogen over here has got to be partial positive because one of the resonance structures has it with a formal positive. And then this carbon over here must have a partial negative. So we could show this as the hybrid resonance view. Does that make sense? All right, let's try a different one now. So I'll do example number 2. All right, for this next example, I'm going to keep it really similar. I'm going to have 2 hydrogens coming off of these carbons, and then CH3. All right, let's try to determine the resonance structures for this. What do you guys think we should do? Are there resonance structures?
No.
Why not?
Don't worry about it.
Yeah. This is one of the most common mistakes I see is an organic student will say, let's move this or this lone pair over. They'll say, all right, let's draw this. This now has a CH3 here. Now we've got a carbon, carbon, CH3. Got 2 hydrogens here, 2 hydrogens here. This nitrogen has a formal positive charge. That carbon looks really wrong, right? Do you guys remember what I call these carbons? Texas carbon. And then I'll give you a frowny face. So please don't draw these. They're not valid at all. That carbon can't have electrons go into it because it already has a full octet. So going back again, what hybridization must this nitrogen have? It's got to be sp3. It doesn't have the potential to delocalize, so it can't. So it is a little bit tricky. On the first quiz, all you had to do is look at steric number. Now you need to look at steric number and determine whether or not you can actually push those electrons around. If you can push those electrons around, it may change the hybridization a little bit. Does that make sense? All right, so now what we've got to do is assess the relative priority of various resonance structures. So like I said, not all resonance structures are equal. Sometimes they are, and if they are, they're referred to as degenerate, but occasionally one's way more important than the other. So let's go back and talk about that. So rules for determining relative priorities of, or relative importance, I should say, of resonance structures. These rules are pretty straightforward, but I'm going to list them in order of priority. So number one, first thing you want to look at is whether or not each of the atoms in the molecule has a full octet of electrons. So I'll say full octets take priority. So an example some of you saw during the review session was with carbon monoxide, where they say, all right, carbon monoxide, if we look at it, can be drawn like this, where the carbon has a negative charge, the oxygen has a positive charge. And a lot of people say, well, oxygen's really electronegative. Why the heck is it carrying a positive charge? Shouldn't we try to alleviate that positive charge somehow? Shouldn't we take these pi electrons and move them over? If you do that, you end up with a structure that looks like this, where technically that carbon has a neutral charge and the oxygen's neutral too. But what's wrong with this carbon? Doesn't have a full octet. So you could draw this, but this is very minor. The carbon doesn't have an octet. This one is going to be our major contributor for carbon monoxide. So that's important to look at. All right, if you're tied and you really can't tell beyond that, then you need to follow rule 2. If tied, the structure with minimized charges is going to be more major. Whoop. That's a pretty simple one. Molecules want to be uncharged if at all possible. So those would be the major contributor after that. All right, if still tied, then look at electronegativity. So for example, the major structure, or I'll say major contributor, will have, excuse me, a negative charge on the more or less electronegative atom. The more electronegative atom. That makes sense. We know electronegative atoms are happy carrying negative charges, so that will be the major contributor. Alternatively, the major contributor will have a positive major contributor will have a negative charge on the more electronegative atom.
And then the minor would have the positive charge?
Yeah, this is another way of thinking about it. So major contributor will have a positive charge on the least electronegative atom. Sorry. What's that? Am I spelling it right? Okay. Making me second guess myself. All right, so you want to look at electronegativity. Ideally, you want the negative charge to be on the more electronegative atom, but if you don't have negative charges, you want the positive charge to be on the least electronegative atom. Number 4 is a pretty simple one. Avoid structures with carbon that has a positive charge and carbon that has a negative charge. We typically don't want to draw those. So I'll show you an example of this. Yep.
You mean avoid structures that have both at the same time?
Have both at the same time. So a good example of this would be ethylene, where you've got a carbon-carbon double bond. You're technically not breaking any resonance rules by moving this pi bond over to a carbon. If you do that, though, this carbon on the right now has a negative charge, and the carbon on the left has a positive charge. This is super minor, meaning don't draw it. You only need to show that as a localized pi bond. It's really not delocalized to any meaningful degree. Does that make sense? All right, so let's do some practice. What I want you guys to do is to draw the resonance structure, all of them that are available, for this compound right here, where the carbon on the right has a negative charge. So draw as many as you can. I'll give you a hint, there's 2 more. Check with your neighbor, see if you agree, and then assign them from most important to least important structure. So I'll give you guys a minute to work on that. That's a CH2 on the right, and the carbon has a lone pair and a formal negative charge. you think you got it, give me a thumbs up so I know where you guys are at. All right, a few thumbs, a little shaky.
There's 2 more?
There's 2 more. You guys want another hint? One of them has a carbon with a positive charge. All right, let's see a show of thumbs again. Thumbs up if you got it, thumbs to the side if you're still working on it, thumbs down if you're completely lost. It's okay to put a thumbs down. All right, let's take a look at this. This one's a little confusing. There's a bit more going on with this one. So I'm going to do something we haven't seen before but is valid. We can move this pi bond up to the oxygen. This carbon still has a negative charge. This carbon's positive. This oxygen is negative. All right? And then after this, I can take this set of electrons and move it down there and form a pi bond. I'm going to just drop both of these hydrogens now. All right, so looking at these, first thing we look for are full octets. Do any of these structures have atoms without full octets? The middle one. Yeah, if you look at the middle one, it does not have full octets. That means it's got to be a minor contributor. What else is going on with this one that's less than desirable?
C plus and C minus.
It's got excess charge, that's one. And then rule number 4 said avoid drawing molecules with C plus and C minus. So this one doesn't have full octets, and it has a C plus and a C minus. That means that this is very, very, very minor. In fact, you don't need to draw it. All right, so now we're stuck between the side two. Which one do you think is more major between the left one and the right one?
The right one.
The right one? Why? Negative charge is on the oxygen, right? So if you have to put the negative charge on an atom, that negative charge would prefer to be on the most electronegative atom. So I would say this one is our major contributor, and this one would be our minor contributor. And then if we try to draw the hybrid, we're going to kind of ignore that middle one because it really doesn't participate much. And it's going to be in between the major and minor. So I'm going to redraw it down here. We do have some delocalization occurring here. The oxygen up here, I'm going to put a really big delta negative, and then down here I'm going to put a little itty bitty delta negative. This would be our hybrid view of that molecule, if that makes sense. So like I said, not all resonance contributors are equal to one another. Okay, last but not least, I'll give you guys a list of some patterns to look for when you're looking for resonance structures. So patterns to look for. First one I call lone pair sigma pi. So what do I mean by that? Well, we saw in our last example, right here we have a lone pair, right here we've got a sigma bond, and right there we have a pi bond. So that's an example of lone pair, sigma, and then pi. And we know we can delocalize that lone pair down here. It's got a negative charge, and we can kick that all the way up to the electrons. Another example we saw was if you've got an oxygen with a negative charge down here. Again, that lone pair doesn't have to be on a carbon. It could be on a non-carbon atom. That's lone pair, sigma, and then pi. Both of those are allowable, and you can push the negative charge on that oxygen up onto the other oxygen too. So that's a common pattern to look for. Next one is cation, sigma, pi. So we have a couple of examples of that one. The first one we saw yesterday, where we've got a cation, a sigma bond, and a pi bond. So cation right here, sigma bond here, pi bond right there. We can delocalize that. Let's do another one. This one looks a little bit different. So if we look at this one also has a cation, sigma, and a pi. So a cation right here, sigma bond right here, and a pi bond right here. So for example, I can move this pi bond over. And if you do that, you can leave the oxygen put for the time being, and that's fine. That moves that positive charge to the other side. But again, that pattern's still there. There's a cation, sigma, and a pi right there. So that's another common pattern you might see. Requires a different sort of arrow pushing. Another one you might look at a lot is a let me rephrase this, non-carbon carbon pi bond. So let's take a look at an example of this. So we've got acetone right here. We've got a non-carbon-carbon pi bond, right? It's a carbon-oxygen pi bond. We do have resonance structures that we can show with this. Specifically, you can move this pi bond up. Why don't I move the lone pair down? Violate the octet rule. So if we were to draw this, now we've got a negative charge on the oxygen and a positive charge on the carbon. So that's another common one you might see. And then last but not least, we've got aromatic ring systems. And this one's one of my favorites. So let's draw benzene. Benzene's a hexagon with alternating double single bonds. Benzene has an important resonance structure where all you do is rotate those double bonds around. And again, you might say, aren't those the same molecule? Kind of. They're degenerate contributors. However, if we think about it in terms of its hybrid, those electrons are moving all the way around the ring system. You may even see some chemists draw it with a circle inside to show delocalization of all those pi bonds. Those are all acceptable, but it is an important resonance structure for aromatic ring systems. So what I want you guys to do is to work on the pod, ideally with a classmate, double check each other's answers, and if you have time, try to assign relative priority to all your structures. Which one's more important than the others? If you guys have questions too, I'll be in my office tomorrow morning, and you're more than welcome to stop by. I know this stuff is pretty challenging when you're first looking at it.